test it. Um, so if we're looking at our breakdown and our schedule, week 1 is done. We're in week 2. In theory, you've gone through and done the reading journal. You should have done sig figs. What is today? 28th. So you should have looked at periodic trends, and you probably did not do the quantum electron stuff, which is probably going to throw you for a loop. Um, that's okay. It's neat stuff. Um, the hard part for me is that we're talking about that in OChem also right now, so I'll have to try and make sure that I parse that correctly. Um, if you got questions about it. Um, so yeah, so far so good. No extra questions? Yes, sir. And for the sake of the recording, sorry for all the scrolling. Um, and for the sake of the class. So if we're going through and looking at this is going to require you to understand or potentially manipulate this concept of what a pure compound is. So both pure and what compound is. Okay, so pure means that's the only thing present. Okay, that's it. So I can look at a sample of hydrogen gas. Let's not pick hydrogen gas because that starts to ask other questions that I don't think we're ready to answer yet. Let's look at a sample of neon gas. So if I just had neon in a tube, okay, I could look at that as a pure sample, okay, because the only thing present in there is neon. Okay, so it's isolated from everything else. Would I be able to call that a pure compound? Well, what's a compound? Okay, 2 or more elements, which is then going to introduce kind of a new issue. So let's say I have that sample of neon, except now instead of it just being neon, I've got neon and helium. Am I now looking at a pure compound? No. Nope, because if I take neon and helium and I put them into that tube, it will become uniform, perfectly uniform. So that's not going to be a compound. It's 2 or more elements, so why is it not a compound? Nope. What? Yes. Okay. So when we look at this sample that has neon and helium in it, neon and helium aren't chemically linked. They're physically near each other, but they aren't chemically linked. So that when neon wants to move to the left, helium can move to the right without any problems. But if neon moves to the left, does helium have to follow it at a certain distance? Okay, so they would have to have that chemical connection. This is a really challenging concept to address for students right now, because how much have you dealt with chemical connections? You haven't. So starting off a class looking at the difference between chemical and physical, I think is a very questionable approach, but that's how all of our textbooks address it, and so we're kind of stuck kind of dealing with this. Okay, so there's a physical proximity that can happen, and then there's a chemical proximity that has to happen. Our compound is looking at, what did I do? Our compound is looking at our elements, 2 or more, that are, whoa, I forgot I can move stuff around. 2 or more elements, the circles up there, that are chemically linked. Okay. How do we differentiate chemically linked? Okay, so if I looked at my hand, right, that's about how far from my body? 2, just 2? Distance. What's the distance between my hand and the rest of my body?
Like 2 feet maybe?
2 feet. Okay. So this is how I'll learn names. What was your name?
Lily.
Lily. Pleasure to meet you, Lily. Okay. Is Lily closer than 2 feet? Sorry. To me. Yeah. Is my hand chemically linked to me? Is Lily chemically linked to me? But she's even closer than 2 feet. It's feeling really awkward. Okay. But she's even closer than 2 feet. Why is she not chemically linked? How is that different? You can physically separate them, okay, by moving them to different spaces. Okay. Could I physically separate my hand to the same distance that I am now with Lily, which is 20 feet? Okay. Okay, which is the appropriate response? No, unless you like chop it off. You mean that chemical linkage. You're breaking those chemical connections. So when things are physically linked, they can be near each other, but that doesn't mean they're chemically linked. Chemically linked means that they will always move with each other through that whole process to at least a first order approximation. Okay? Kind of, sort of? Yeah. So that when we're now talking about our pure compounds, pure means, if it was just going to be pure, a scary thought, if this room was full of pure compound, where I'm a compound, every single one of you would be me. Yeah. That doesn't cause nightmares. I don't know what does. Okay? That's now looking at a pure compound. So right now within this room, are we looking at a pure compound? What are we looking at? We're looking at the people within this room. If I'm a compound, what do you think you are? You're also compounds. But we're not pure. What are we? So now well, what's the English language that we would use? What's the acceptable language that we would say that we would need to use to describe the collection of us? It's a mixture. Okay? So we would be a mixture of compounds. Okay? That's sort of easy on this macro scale. When we start getting really micro and nano and whatever description you want to use for that, that becomes harder and harder to process. Okay? So let's think about another example. Let's take a look at water. What is water? Cool. So if I look at H2O, I could draw out H2O, which we'll learn later this unit. Okay, but there's my compound of H2O. Compound. Why do I know it's a compound? How do I know they're chemically bonded? How do I know H2O is chemically bonded, whereas when I had neon and helium, they were not chemically bonded? How do you tell? You can physically. You're telling me I can't physically go up there and grab the letters and pull those over there? I mean, not technologically, but hydrogen, I couldn't just stretch that way over there. How do you know they're linked? What is different about how I've drawn water versus how I've drawn the neon and helium? Cool, I drew them together, like spatially. So if I go through and do this, does that change my depiction? I didn't mean to change the color. No. So spatially, didn't matter, wasn't relevant. What is different about my water box versus my helium neon box? The number, well, there's different numbers of particles, but I could go through and just add another helium. That's going to get me the same number of particles. Okay. You're saying structure, but I don't know what structure means. It's the lines. What do those lines represent? A chemical bond that connects those atoms. If I go through and look at the neon and helium, I'm not showing a line. Why not? Because they aren't chemically linked. Okay? What if we switch this up? Because we got to test all our limits on this. What if I did H2O? Now how do I know H2O, I'm talking about the compound, whereas neon and helium, I'm not? That's way harder. Because you don't get to see any of the lines saying, oh, I don't have a chemical bond. I haven't shown a chemical bond. How do I know H2O is the compound and neon and helium is not? Fortunately, not a bad idea, but no. And this is going to double back to Matthew, right? Okay. One of the things you were talking about was just the spatial relationships between them. Look really, really carefully. And if we look at the, stop moving. I was going to say, like, I know technology. Apparently I don't. Look at the space in here. See the little yellow there? The space in there versus the space in there. What do you notice is the difference? There's a little bit more space in that bottom one. But what if I had deleted that space? Let's not do yellow. Give me my freaking colors back. What if I'd done that? Now it starts to look like a bond. How do you know it's not a bond? This answer is going to suck. It's a horrible question at this stage in the game, just for the full disclosure. How do you know that there's not a bond when I draw neon and helium that close? You don't. That's fair. You don't. Okay? I know because I know something about the chemicals themselves to know that those would never link. Okay? Which means when I try, or when any chemist tries to teach this chemistry, what do we have to do to try and help you out without having to teach you all that chemistry? We better make sure that we provide a little bit of a space in between to emphasize the fact that they are not chemically linked. Okay? So what you are looking for to define that in a formula system is literally empty nothingness. Is there empty nothingness? They're not chemically linked. Are they really close to each other? They're chemically linked. Kind of, sort of? Yeah. Okay. Which then pushes us back to the question. The question then sidesteps all of that, okay? Mostly because at this point in the class, we haven't talked about chemical formulas and I got ahead of myself. Okay? And instead, it gives you a bunch of these examples and says, okay, given these examples, how are these pure compounds or are they something else? So we already talked about one other thing. They could be a mixture of compounds. Okay? They could also be pure elements. They could also be a mixture of elements. Right? So we get all those kind of possible combinations. So you have to understand what the pure means. You have to understand what the compound means. And then you have to apply it allegedly to a real world scenario. Okay? I don't like this question. Okay? And if you dig into chemical education research, a lot of people don't like this question. Okay? And why? This becomes the fun one. How much chemistry background have you had? Okay, maybe a week. What is air? It's oxygen. No, it's not.
Air is a mixture of oxygen, like whatever's in the air.
Okay? You don't have any chemical knowledge. At best, maybe you understand that you're alive and we need oxygen to breathe, so you say there's oxygen in the air. Yes, there's oxygen in the air. But if we went through and said, what is oxygen or what is air? The majority of air is not oxygen, it's nitrogen. Do you know that when we say air, do you know the composition of air? Okay, you don't. That's going to be really hard for you to answer this question. Okay, we kind of say, well, everybody should know what air is. Okay, but what about pickle juice? Have you had a pickle before? Somebody, oh yeah, those are the best thing ever. Other people are like, what the hell is a pickle? Okay, not everybody's had a pickle, so how would they be able to answer what pickle juice was? Okay, and even then, if you've had a pickle, what is pickle juice? Damn, we're right back at that same problem. How do we figure out what's supposed to be in it? Okay, and this becomes this weird gray area. So why even ask this question? Because this question is going to be asked of you. Okay, it just is. And so what we're trying to get at is for you to process as best as possible what's going on within it. Okay, we kind of make the assumption you understand a little bit about what air is. Okay, even if you assumed it was just oxygen, you've been around in Arizona during the summer. Is it just oxygen that we see in the air? What else do we see? We get rain, we get dust. All of those are in the air. Okay, so if we're going to say all of those are in the air, is dust the same thing as oxygen? No, this is why you can't just stick your head in the sand. It doesn't work. Okay, and live. Okay, so that can't possibly be a pure compound because both dust and oxygen don't do the same thing chemically. So air doesn't make sense to be a pure compound. Well, how about pickle juice? Anybody know how you pickle things?
Vinegar.
Cool, vinegar. What is vinegar? Let's avoid that because some people added some extra things. It's not just vinegar, it's also salt. Okay? Are vinegar and salt the same thing? No. Okay? So if I'm going to look at pickle juice, I know I have two different substances in there. That can't possibly be pure. Which then takes us to water. And water is unfortunately really gray area because you go, oh, water, I drink water all the time. Are you drinking just water? Okay? No. Okay? This is why you can taste water and it tastes different because there's other stuff there. But you're now talking about tap water, not water, the compound. So water now floats in this weird gray area of what water are we talking about? We aren't talking about tap water, we're talking about just water. Well, what is water? You all said it already, it's H2O. And so if I'm going to talk about water, I'm going to talk about H2O. Okay, well, if I write that out, the H, the 2, and the O are all real close to each other, which then means I have two or more elements that are chemically linked because spatially I've put them next to each other. I don't know what that button was. Okay, which then means they are a compound. And since I haven't defined this as salt water or tap water or drinking water, we're assumed that that's the only thing we've got, which then by definition makes it a pure compound. Kinda?
Yeah.
Okay. So where I want to get with that is a livable interaction. Are you livable with that explanation? Because you should not be happy with that explanation.
I just have one more question. So if air is like everything that's in a room, could that, for question 5, could that be classified as a homogeneous mixture, or is there no way to tell what, how much is in what?
Cool. So 4 and 5 kind of tie to each other. So 4 is bringing this concept of pure ultimately versus mixture and compound versus element. Okay, that's what question 4 is about. If we move to question 5, it's now talking about mixtures. Okay, and we can say mixture versus pure, but now we're saying explicitly mixture, but now we're adding another word. We're adding homogeneous versus heterogeneous. Okay, and so for the record, as we process this and we talk through this, we're not trying to answer the question. What we're trying to say is what are all the possibilities that could get asked? Because when you get the exam, are you going to get either of these questions? Probably not. But what you might get is which of the following is correctly classified as a mixture of elements. If you studied the concept behind the question, you're golden. If you studied the question, you just shafted yourself. Kind of, sort of? Okay, so question 5, we're in the mixture category, but now we add a new term, homogeneous. Homogeneous versus heterogeneous. What is homogeneous? The same, okay? That's ultimately just the root word of homo, and hetero is different. Okay, I don't know what the root is for genius, but we're just going to assume that I'm right within this. We're talking about the phase. So if I say homogeneous, what am I saying? All of the compounds that are in my mixture are in the same phase. Okay? Heterogeneous would mean they're in different phases. Okay? So if we take a look at salad dressing, okay? Some people don't use salad dressing. They're like, how the hell do I answer this question? Unfortunately, yes, you're stuck in that boat. So, what is salad dressing? Somebody look at it. Sometimes it depends, but for the most part, you've probably looked at it and you should be able to classify it. If you just look at your salad dressing, does it look like one thing? No. Okay, why not? So we could go with oil and water. There's herbs. The herbs are a solid. The oil is a liquid, which means two different phases. Salad dressing is going to be heterogeneous. Okay? Then we get air. We'll go back to the air example. Okay. Well, what air are we talking about? Are we talking about the air in the room? Are we talking the air during a rainstorm? Are we talking about the air when it's really cold out? Are we talking the air during a dust storm? Yeah. Okay. That could be a question. You raise your hand, Mike. What air are you talking about? I'm gonna be like the air in this room. Okay. What are the phases of the air in this room? It's a gas. I have oxygen gas. I have nitrogen gas. Probably have some helium in there. Okay. Probably some methane, believe it or not. Okay. They're all gases. Can you point to the different phases of the air in this room? No, which means homogeneous. They're all the same phase. Does that make sense?
Yeah. So is salt water homogeneous?
I skip salt water for a moment. Okay. Let's look at what could water be heterogeneous? Yeah, think back to our dust storms. This is the most relevant case for us. So if we look at the dust storms, what do we see? We've got air. It still has all the oxygen and nitrogen in it, but it also has all the little solid dust particles floating through the air. That's a mixture of solid and gas. That's heterogeneous. But typically, we aren't breathing heterogeneous air. Does that make sense? The one I like to pick on is fog, which is fun because we live in this state and very rarely do anybody know what fog is. But those people that have seen fog, is that homogeneous or heterogeneous? Has anybody seen fog? Should we try that? Okay. I think there was a foggy day earlier this year, but no one's awake then either. But in any case, when you look at fog, what do you see? Okay. And this one becomes interesting because it's usually a uniform, like white cloud. And if it's uniform, we tend to go, oh, uniform is homogeneous. And that's where we have to differentiate those terms. Those little dust or those little white fog that you're seeing is actually what? Water particles. They've condensed. They're small enough that they're floating in the air. So fog is actually a mixture of liquid water and gaseous air particles. And it's the combination of both of those that's allowing us to have that fog effect. If you want to learn about fog, it's kind of a neat process. You should take a geology class because they talk, or geography, one of those two. The geosciences class teach about fog and when it comes about and all that kind of fun stuff. Okay? Which then takes us back to the challenging one, salt water. Okay, what happens when you add salt to water? Okay, so we're going to get a lot of different descriptions to this, but ultimately think about beginning and end. I start with solid salt and liquid water. I add them, what do I see at the end? Okay, do you know it was just water? And that becomes a challenging. Okay, so we just see a clear liquid looking thing, right? Okay, what happened to the solid? It dissolved into it to make a homogeneous solution. Okay? But this is where some smart aleck will be, okay, I'm going to take a kilo of salt and a drop of water. Like, I still got the liquid water. I just can't see it in all there. Is that still homogeneous? No, it's not homogeneous now because the scale is way off. So with these questions, we run into what is a reasonable scale behind it. Okay? So thank you for asking these because hopefully we've set a limit now on what that scale might be. Ish? So, homogeneous mixture. What did we say about salad dressing? We said that that was heterogeneous, which means not an answer. Salt water. Was that a homogeneous mixture? Was it homogeneous? Yes. Was it a mixture? It had salt and liquid water. So yes, that's a mixture. Okay, air. That is homogeneous and a mixture. I have oxygen gas and at a minimum nitrogen gas flowing through that system. So in this particular scenario, and we may encounter a problem here, we'll see in a second, both B and C are valid. Well, dang, how can I possibly answer that question if both of those are valid? Hopefully, we continue to read our answer choices and we see, oh, thank goodness. Okay, there's an answer choice that says B and C are valid. That would be the one I would circle. Okay. For number 4, which of the following is classified as a pure compound? The pickle juice we said was not a pure compound. That was a mixture. Okay, which defeats the purpose of pure. So that one's out. Water, we said it was just H2O. So yes, it's a compound because I have more than 2 elements that are chemically linked because spatially they're next to each other. And we run under the nasty assumption that we aren't saying there's anything else there. We're not calling it salt water. We're not calling it bath water. We're not calling it tap water. It's just water. So water would satisfy our pure compound for question 4. Okay, air, we just said was a mixture. Okay, so that doesn't qualify as a pure compound because it's a mixture of compounds. So 4 should be, I already forgot, just B. Does that make sense? Do you see all the permutations behind how you should think through this? Okay, which sets up a question for what should you do for your paper homework? Okay, so if you were going to go through and say paper homework was doing this, let's look at 4. Does it make sense just to do circle water? No, what should you do to define this process? What are you explaining? Are you saying water is a pure compound? I'm sorry. Okay, why it's a pure compound. So what I would argue there, what you're doing is you're looking at pure and saying your options for pure are either pure or mixture, right? Pure is chemical. Come on, pen, work with me. Oh, if I write harder, it gets bigger. Okay, chemically, mixture is physically. If we look at a compound is 2 or more elements. Or what's our other solution? Our other option? Just an element. Okay, a single element on its own. If you did those 2 parts, just what I've written up here, I'm kind of okay with it. You've addressed the concept of what pure is talking about. You've addressed the concept of what compound is talking about. You're then going through and saying water matches that best. Okay, and you could go through water's a pure compound. No value add. What else could you add to this to actually make it better? Nope, which is why when we say compound, we're saying what are our 2 categories that it could boil into. So, good follow-up. Just like with pure, pure could separate as pure or mixture. And I didn't do that very well with the compound one. What else could I add to this as a follow-up to help with my work?
Specify that the answer is not going to be A or C because those aren't pure compounds, they're mixtures.
Okay, so the answer can't be A because pickle juice is not a pure compound. Couple things I would complain about on that. One, you just said it was not the answer because it's not the answer, right? Okay.
But if you added the 2 extra pieces to that, would that be okay?
So where I would go is a couple statements. So number 1, your explanation isn't very nice. You're also using complete sentences. Okay, do you know how to use a complete sentence? Is this a class that requires complete sentences? No. Okay, so don't worry about that. What was pickle juice? We're hearing some people say it was a mixture. That was a mixture. Is that a pure compound? No, because it's a mixture. Done. I've added a next layer of information to prove that I understand what's going on with that. What's air? I can add a complete sentence and I can say pickle juice is a mixture of vinegar and salt. And garlic and peppers and dill and whatever else you want to add to that, that's fine. Okay, but we don't need all that context. As long as you've identified what it is, you're now showing you understand the concept behind that. Does that make sense? That's now acceptable for a paper homework. Make sense? Okay.
Would you say would a good answer be only water because it's the only option that's elements with chemical?
What is vinegar?
Vinegar is a mixture, it's not an element.
No, unfortunately, vinegar is CH3COOH, which is they're chemically linked. That's a compound. Okay. So if you're wondering, like, well, dang, how'd you come up with that? More experience, number one. Okay. And number two, okay, how would I know that vinegar is a compound and not an element? Let's flip that on its head. How do you know vinegar is a compound and not an element? You only know it's more than one element because I wrote the formula. How do you know vinegar is a compound and not an element?
It's not on the periodic table.
There it is. Remember that memorize your elements thing? Was vinegar one of those things that was listed? No. Why not? Because it's not a flippin' element, it's a compound. So you do know that. Okay? That's challenging. Process of elimination, but you have the feedback to allow you to come to those steps. Whether or not you recognize that you have it is a different question. Make sense? You good, Matthew? Because you had a couple follow-ups on that.
I think so. So I'm trying to. So if. Okay. So but I do know. So if I do know that pickle juice does not have pure elements, meaning that it's a mixture, and water is the only one. Like I'm trying to really nail down like what a pure compound is. It's a one that has pure elements chemically bonded.
Pure just means that it's a single entity.
Right.
Whatever that single entity is. That
Whereas,
everything is either connected, and when you look at the individual connected pieces, everything that shows up is the same connected piece.
okay, whereas pickle juice and air have things at different stages and all sorts of. Okay.
Different states, and they don't even have to be different states, because if we actually look at it, vinegar is a combination of acetic acid, which I drew up, and water. Okay? Those are both in the same phase, but they're mixed together. They're not chemically linked, they're physically linked. Now, if we say tap water, now tap water has a bunch of other stuff in it. Okay? Which is why, if you ever have to clean out your sinks or showers, there's usually a mess because there's a bunch of crap in your water.
So it's everything in a pure compound is chemically linked to each other.
Each individual unit
Individual unit. Okay.
is chemically linked. Yes.
Sorry, I know he followed up on this, but I was a little confused on that, where you explained that a compound is two or more elements chemically linked, but then why did we put or element?
No. As soon as he asked it, I was like, I should clarify that because it's not clarified well. So when we did the pull down for the pure, what we were saying is our options for pure could be pure or mixture. When we look at the word compound, that could pull down into two categories, either compound or element. Or a compound is two or more elements chemically linked. An element is an element. Are we okay with that definition? Okay, good. I don't have a better one. Is just an element. Does that help to clarify that?
Okay.
So what we're trying to say is, what are the key words? What were the options that those words could be changed to? So when we look at homogeneous, what were the options our word homogeneous could be? This could have been homo, or it could have been hetero. So what you're effectively trying to do is predict, how does a lazy instructor look at this question and go, how do I change this the smallest amount possible so the same answer isn't selected? Okay. That's a little metacognition for you, thinking about how the instructor is going to work on things. And believe it or not, every single one of your instructors is lazy. Some of them are more lazy than others. Pretty lazy. Which is fun. I just realized that when I like mumble something to myself, the majority of the class can't hear, but I'm pretty sure the recording picks it up. Did you have a question? Was it your hand? Okay, I thought I saw another hand in the back. No? Okay. So what do we want to look at? Are we good? Okay. What do we want to look at?
It's not on this topic anymore.
Yep.
Okay. I was watching the lecture last night on I don't remember exactly what it's called, but quantum is in the title. And so I'm just trying to it's about the different wave frequencies of light, if I have the concept correct. That it's short wave when they're closer together, and longer wave when like the bumps or waves are spaced further apart. Is that correct?
So, and I always have to draw it because I'm shaky on it. So when we talk about light, number one, light, for the record, this is now the lecture that you're supposed to watch, I think, tomorrow. Is that right? Okay. So we're pushing a little bit on what the class has seen. But when we talk about light, we have to break down what light is and how it kind of relates to things. Okay. The first thing we want to address is that light, or how light moves. Light moves in a wave. Were all waves the same? No, because I could have that wave and I could also have that wave. So what I want to be able to do is to look at those waves and break them down so that I can talk about certain aspects within them and have the language to represent it better. Okay, so there's a couple pieces that we would look at. Okay, number one, we could look at the distance from peak to peak. That distance, I want to associate a name, because in the bottom one, it's a shorter distance, and the top one, it's a longer distance. Okay, so instead of just saying, hey, that peak to peak thing is changing, I want to say is changing. I can make up whatever word I want to do for this. Okay, but what are we measuring there? Are we measuring volume? We're measuring a distance. We're measuring the distance on what? A wave. So what do we want to call it? The wave distance. Oh, I know, wavelength. Okay, so that's now referencing the wavelength. Okay, so we could now go through and look at that top line having a longer wavelength than the bottom one. So it's just trying to break down that composition. Does that kind of make sense?
Yeah.
Okay. There's other parts that we can get behind this too, is not just the wavelength. We can talk about for a given span of distance or time, it's usually time, how many peaks did I get? Okay. So what I would do is hold it constant, and I would say from this point to, let's go this point, same for both, how many times did I get a peak? Okay, so for that top one, within that distance, I got 2 peaks. Okay, within the bottom one, I got 3 peaks. So what we're talking about is the frequency at which I get those peaks. Okay, so the number of peaks per a unit, usually a unit of time. Okay, this is what's known as our frequency. Okay, radio waves are waves. Okay, so how are light and radio waves connected? Or are they? Radio waves and light waves are the exact same thing. Okay? So we could say, well, so everything is light? Well, when we talk about light, what do you think about? Light, what's the... we gotta be careful with electricity. Illumination, kind of getting to it. If if I flipped the switches in here, what would you tell me about the light? Oh, it's dark, which means there is no light. What is the light associated with? It's your vision. Can you see radio waves? No. Ooh. Okay. So by calling them light waves, the natural reflex that everybody's go, oh, if radio waves are light waves, I can see radio waves. No, you can't. Okay? Light has that kind of connotation associated with it. So instead we take a step back and say light waves and radio waves must be part of something else that's a larger continuum. Okay, that larger continuum is that when we look at these waves, I can have really, really, really long wavelengths and I can have really, really, really tiny wavelengths. And when I hit certain ranges, I'll go through and say, ah, that range is a radio wave. That range is a light wave. That range is gamma radiation. You're like, dude, how they make the Hulk is the same thing as light? Yes. Okay, exact same principle. You're just looking at different changes to your wavelength and frequency. When you change those, that changes something, some other characteristic, because they're contributing to another characteristic that we would want to pay attention to. Okay, which we'll get to in a second. Okay. Everybody's inherently lazy. I don't care if you think I'm wrong. Everybody's lazy. Nobody wanted to write wavelength. Way too many letters in it. So what do we have to do? We want to come up with an abbreviation. What's the abbreviation? WF. Okay. I guess you're missing the T. Okay. We can make whatever we want. Whoever first discovered and quantified it and sold this knowledge to everybody else got to define what that term was. When we talk about wavelength, the term that they picked or the symbol that they picked was the Greek letter lambda, which I'm sure you can draw better than me, but that's what it is. When we talk about frequency, what did they pick? The Greek letter mu, something like that, which usually gets abbreviated as just a V. It's not a V, it's a Greek letter frequency thing. Okay? Those are the standard symbols that are typically used for wavelength and frequency. Okay? Could I quantify them? Yes, I absolutely can. Okay? I don't need you to quantify them. I'm not asking you to run any calculations with these. I just want you to be aware of what those things are. Okay. Why is it important to know what's going on with our wavelength and frequency and that they're connected to light and gamma radiation and radio radiation? Okay. Because when we put those things all together, they contribute to another factor that we would go through and see and be able to monitor. If I hit you with gamma radiation, are you going to be upset? Yes. Why?
You'll be dead.
Why would I be dead? What's that? It's stronger. Okay, what's stronger? What are we talking about? The energy. The energy of gamma radiation is so high that when it hits you, it's going to start exploding parts of things off of you. Okay? But when light energy hits you, what happens? Nothing? Really? If nothing happened to you, would you be able to see? No. Which means light is actually doing something. When it hits your eye, it's hitting a molecule in your eye, and that molecule, instead of being straight, bends. That change in shape is enough to signal your brain and say, hey, this color hit this section, this pixel in your eyeball. Make sure you show that to the brain as being an image that you're now going to see. That's dealing with in the retina, cornea, all that fun stuff. That's a biology class. I don't care about that. Chemistry, straight bend, straight bend. Okay? That's all it is. What happens when radio waves hit you? You can hear radio waves? What is 94.9 playing right now on the radio? They're all over the place. Okay, I just picked a random number. Okay, we aren't hearing the radio waves. So when you're saying you hear radio waves, what's happening? A receiver that we designed as humans hears the radio wave and turns that into sound waves that our ears can pick up as the vibration. You're not hearing radio waves. What you're hearing is a vibration created from the speaker. Okay, so are radio waves things that are impacting us? Okay, right now, we're assuming the answer is no. We really want it to be no, because 94.9 is blasting out radio waves. Okay, and those radio waves are impacting us whether we want them to or not, and we know they're impacting us because all I got to do is pull out a radio, tune it to 94.9, and the speaker starts making sounds. Those radio waves are coming through. Okay, but for the most part, they don't affect us. We haven't seen any effects for humans or really anything within radio waves, so we don't stress about it. Okay, but when we look at the entire range of wavelengths that are possible, there are certain areas that do more damage than others, and so we want to be careful how we deal with those. Like gamma radiation, we don't want to see that, okay, which really only happens in a couple spaces, in a research lab where they're flipping crazy, or in space. Okay, we tend to not get gamma radiation here. Why? That's our atmosphere interacting with it so that we don't feel it. Because if it hits us, we're toast. Okay? What other parts are part of that spectrum of energies? We got radio waves, we got light waves, ultraviolet, microwave, X-ray. All of those are different parts of the spectrum, and all of those have energy associated with them, and that energy can cause different things to happen. Why is that cool? Because I can leverage that to do different things. Like microwaves, I can leverage to vibrate my water molecules. And when my water molecules start moving around, what happens? They get hot. And so I can heat stuff up. Right? That's also why it stays in that little box, because if it was aimed at you, it's going to cause the water molecules in your body to vibrate and heat you up, and not in a pleasant way. Okay? So that whole range of all those things is known as the electromagnetic spectrum. Okay? Or electromagnetic radiation. Nobody likes the word radiation. They think it's dangerous. Light is flipping radiation. Okay? Radiation is just referring to those wavelengths. So that's light. Why do we care about light? Because we can probe different things with light. One of the things that we can probe has to do with that quantum world. Okay, so when we talk about the periodic table, okay, there were trends. Theoretically, everybody watched the video on periodic table and trends, right? Yeah. More or less. So tons of trends on the periodic table. Okay, you're a chemist, now you have to know all of those trends. Okay, and theoretically, that video ended with size, I think is where that ended, right? Because when we look left to right, what happened? Well, let's not do left to right. That one's a weird one. Let's go down. When I go from hydrogen to francium, what happened to the size of the atom? It got bigger. Why did it get bigger? More molecule. Molecule is a challenge because molecule is the same thing as a compound. We're talking about elements, so we can't use that. Wait, electrons? What are electrons? Part of the atoms. You mean when we talk about atoms existing and being different, we have to identify what are the subcomponents that make up atoms. That's our protons, neutrons, electrons, which is why you watched the lecture on what those individual components were first. Then we can say, once I've got those, do I start to see how things can be arranged? Cool, that's now how we get to our periodic table. Now we look at the periodic table and we start to look for trends, and one of those trends that we like to use, everybody uses it, is size. Okay, well, what's going to dictate my size? Why do protons not dictate size? Oh, so it's not just that I have protons, neutrons, and electrons. They're located in specific spaces within the element, and those things change how I would interpret it. All of my protons are jam-packed into a tight little space called a nucleus, right? So if we're going to look at size, the protons aren't really contributing to size. Well, are they? Am I big or small? Careful. Be reasonable. I'm big. Why am I big? Oh, there, she said it. She's like, your height or your weight. So you're saying I'm fat? Okay. There's two ways we could define size. Size gets very dangerous as a topic because we go, oh, we don't want to be fat, we don't want to be short, all those things. And it is what it is. Okay? Are you alive? Good. Are you healthy? Good. Stay that way. Okay? That works. We talk about atoms, there's no healthy anymore. So what is size? Is size my height? Well, they're round. There's not really, I can't do a height. I'm not measuring from the top or the bottom. Okay, ooh, so it could be the mass. What's the mass of an electron? It's so small, it's 0. So you just told me size was based off of electrons, and she just said size was mass, which means you're wrong. She has to be right because she said size was mass. And since electrons don't weigh anything, they're not contributing to the mass. Ooh, that's not right. Okay, why is that not right? You just know it's not right. Okay? This is where language betrays us. Okay? Because again, we go through and say size, and size meant both weight and height. It was ambiguous. We can't be ambiguous with our language here. Okay? When it comes to the elements, what dictates size? Not its mass, but the volume with which it occupies. Effectively, its height. Okay? So electrons versus protons. Well, where are the protons? Itty bitty tiny little space in the nucleus. Is that really contributing to size? Size is the giant volume. So what's contributing to the giant volume? That's the electrons. If I want to talk about the mass of the particles, yeah, I'm going to talk about the number of protons and neutrons. Okay? But if I'm going to talk about size, when we talk about size, we're talking about the volume that element occupies. That volume, for the most part, is dictated based off of the electrons. So when I look at hydrogen, it has how many electrons? 1. When I look at potassium, let's do potassium because you're supposed to know that one. 19. Potassium begins with K. Good job. Potassium as our element is K. For the record, if you're spelling it, it's with a P. Okay? But potassium is K. It has 19 electrons. Which one was bigger, hydrogen or potassium? Potassium. Why? It has more electrons. We good with that? Yeah, we love that example. That makes perfect, legitimate sense. Let's drop a row down because we get a little bit more. Let's look at lithium with 3 electrons. So Li. Everybody on the same page? Cool. Max it out. Let's look at neon. How many electrons does neon have? 10. Based off of what we just discussed, this is a challenging question, particularly if you did a good job paying attention to the lecture video. So stop paying attention to the lecture video, what we just discussed. What dictates size? Number of electrons. Which element is bigger, lithium or neon? Based off of our rules that we just addressed. Neon, because neon has more electrons. And yet Matthew is right. Lithium is bigger. How does that possibly make sense? Oh.
The shells, the electrons are further away.
What dictates size? Okay. What we started with was the number of electrons. That is entirely patently false. It is not the number of electrons. Well, what dictates radius? It's where your electrons are. Okay? So what's going to control that? It has to be tied to electrons in some way, but it's not just that we have more or less electrons. Okay? This is where the quantum realm comes in. Okay? Electrons are so small that the laws of physics just kind of go haywire on us and we have to create a new physical reality. This is why all the Marvel movies can just say, oh, quantum did it, because nobody can challenge them, okay, and make any sense. Because anybody that challenges them sounds like stark raving lunatics. They probably are. Physicists are a weird bunch. Okay? So how do we see this? Well, we see this because we can go through and I can take an element, hydrogen, it's a nice gas. Let's not even do hydrogen because you've probably seen this before. Let's take neon. Talked about neon before. I can put it in a glass cylinder, a nice little tube, okay, and I'm going to put 20,000 volts into it. What happens if you sat on 20,000 volts? Before you die. Okay, like you sat, whoop, what are you going to immediately do? You get excited. Guess what our atoms does? They get excited too. Okay, the question becomes is what part gets excited? Well, the part that gets excited is tied back to the energy that's coursing through them. Okay, and it turns out when we pump 20,000 volts of electricity into neon, what ends up happening is the electron gets excited. And the electron, instead of being nice and happy near the nucleus where it can cancel out the charge, goes, oh my God, I've got way too much energy. And since it has way too much energy, what does it do? If you have way too much energy, what are you going to do? You're going to be running all over the flipping room, right? Okay, that's way too much energy. Eventually what happens? You calm down. Okay? What's happening to the electron? Yes, it has way too much energy, and eventually it calms down. If we think how we calm down kind of like, we just progressively reduce until we get that lower energy. It's not just, I'm running max speed, and all of a sudden, nope, I'm sitting. That doesn't happen. Okay? It turns out that if that was the case, when we looked at how that electron relaxed back down, what we would see is every step down, it's going to emit energy. And we would see a spectrum of light. We would see all the possible wavelengths as it slowly calmed back down. Or we'd see nothing. And instead, what we saw was bands of light. So that when I looked at helium, I didn't see a spectrum of colored light. I saw a red light. And only a red light. And not just like a broad range of red light. I saw a single wavelength. I saw, I don't know the numbers, 692.43 nanometer energy light with that wavelength. Which means it couldn't possibly be slowly cooling down. What did it have to do? What did it have to do if it didn't slowly cool back down? Had to jump. It's not going on a nice smooth ramp. It's going from one energy state to next energy state. There is no in between. And that difference in energy corresponds to that light. Which means my electrons aren't just willy-nilly wherever they want. They are at discrete energy levels. Those are effectively stairs. So when we look at electrons, they're not just a soupy mass. Plum pudding model goes out the window, right? This is when we talked about Rutherford, where electrons are. They were in discrete energy levels. So when we add that bunch of energy, it maxes out, but then it does jumps. And each of those jumps releases light energy. So instead of seeing a spectrum of energies, I see bands. Those bands correspond to the distance of the jump. Okay? So now we need to go through and say, well, what are all the distances it can jump? And we now have to quantify each of those little steps and stages. That's quantum mechanics. Quantum mechanics is going through and saying, this is where the electron can exist. It can also exist here, here, here. These are all the steps that I can navigate through. Yes, sir.
So there are also, so are there other things like just you have a certain amount of
Well, adrenaline's a slow slope. It's not steps. Yeah. So this, yeah, those steps aspects are really unique to quantum mechanics. Almost everything in your real world existence is going to be a ramp. It's going to slowly slide down. Or it could go slow down fast, but it's still a ramp. It's a continuous ramp. Okay? So on the stairs, okay, it's kind of hard for everybody to see, so let's pretend to draw it here. There's the stairs, right? Here's me, top of the stairs, right? Then I can exist where? I can exist at this step. Let's not draw a cliff. There's another step. I can exist right there, right? Okay. At any point, can I exist right here? Can I just be there? No. I'm either on the lower step or I'm on the higher step. I'm lucky I made that. Okay? There is no middle ground. We're at those steps. That's it. Electrons do effectively the same thing. And we know that because 20,000 volts, they jump, and what do? They spit out light. So this is why when we pump 20,000 volts into a tube of neon gas, we get purple light. You get neon lights. You heard of neon lights? That's exactly what's happening. You're like, but they aren't all the same color. Why aren't they all the same color?
Electrons in a different stage.
It has to be emitting different light waves, but if it's all neon, how could it possibly be different energies? Because they're all the same energies for neon. It's because it's not all neon. They're different elements. So if I want a different colored neon light, I'm not using neon anymore. I'm using an argon light. I'm using a xenon light. Every one of those elements has a characteristic color associated with it. And when I break that color down through a prism, lab next week, okay, you can see the individual lights. Those are the steps that are happening. You can do all sorts of mathematics, yay mathematics, to define all of those pieces. You don't need to do that. You just need to acknowledge that those steps exist, and those steps mean that our electrons exist at certain energy levels. When we deal with the quantum realm, our energy levels go to varying. Is that clock even right? I don't know what I'm looking at. Where are we? I saw some people getting restless. 12:30? Okay, cool. Another hour left. Oh, where our electrons can exist. The quantum realm is going to now define where those things are. And the first place we would start, okay, just like with our stairs, is what are those max level stairs that I can hit? Those would be my energy levels. Okay? Does the periodic table have that information encoded in it? Okay, we're talking about where the electron exists, right? So where do you think hydrogen's electron exists? Take a guess. Wild guess. What energy level do you think your hydrogen electron is going to be at? Why do you think it's the first level? That's a lovely guess. That's amazing. Okay, looking at the element box, no, it doesn't, because that's telling us the number of protons, indirectly the number of electrons in a neutral hydrogen. So unfortunately not there. This periodic table actually doesn't clearly encode it. Some do clearly encode it. Why would hydrogen start at the first energy level?
Isn't the most basic element?
It only has one electron. Where do you think your one electron is going to go? Should your one electron go to the highest energy level or the lowest energy level? It should always go to the lowest energy level. Since hydrogen's the beginning, it's the lowest energy level. It's 1. Cool. Where do you think helium's electron goes? Because helium has now got 2 electrons. So 1 is going to go where hydrogen's first one is. Where's the next one going to go? It could go a step higher. Okay, that's a possibility. Which then means when we get all the way to 118, you're saying there's 118 energy levels. Why are you shaking your head? Does that sound kind of gross? Yeah, it sounds a little gross, a little far out there. Okay, I would agree. Okay, and if we play around with the mathematics, again, you'd have to go back to the mathematics and figure all this out with waves and probability spheres and all of that. Yeah, that gets a little gross. That doesn't work out. It turns out hydrogen or helium's second electron goes to the exact same energy level as hydrogen. Okay, so that's fact. Does the periodic table tell you that? Yeah? How does it tell you that? How does the periodic table tell you that helium's second electron goes to the exact same energy level as the hydrogen? It's in the same flippin' row. Lithium has 3 electrons. Its first one is going to go in the first energy level. The second one's going to go in the first energy level. Where's the third one go? Second energy level. How do I know it goes to the second energy level? It's in the flippin' second row. So how many energy levels are there? 7. Sweet. So we now have our energy levels. Okay? Based off of hydrogen and helium, how many electrons do you think fit into an energy level? How many electrons fit into an energy level? 2, right? Because hydrogen, then helium, and then what do? We move to the next energy level. Oh, this is lovely. I like this. We look at lithium, adds a 3rd electron, second energy level. That makes sense. The first energy level was full. Okay? Then we do beryllium. We said an energy level holds 2 electrons, right? Same energy. That's perfect. We move over to boron.
Same thing. It's still the same energy.
It's in the same row, but you said I could only fit 2 electrons in an energy level. Isn't borons also going in the same energy level? Yeah, it's the same row. But it's shaped differently, right? There's this big open space. Why is it shaped differently? That's because, again, when we deal with the mathematics behind this, every time you go up in an energy, and I know I'm going down with my hands, but every time you go up in an energy, you gain a new type of orbital. So the first energy level is where I can place my electrons. Where I put an electron, I will define as an orbital. Okay? So for that first energy level, I can only put 2 electrons because I only have 1 orbital. When I move to the second energy level, I'm going to get the same type. I'm going to repeat that type, but this time bigger. Right? That's it. So it repeats. So I'll go from that first energy level to the second energy. I repeat the first energy level. So I get one that can hold 2 electrons.
Does it go up to 8?
Okay? But if I continue across that row, I have to account for 6 more electrons. So what does that mean happens? When I move down or up in energy and I get to that second energy level, not only do I repeat what I had in the past, but I also need something new. That something new is not a new energy level because it's in the same row. So it can't be a new energy level. It's going to be a new orbital. Okay? That new orbital can still only hold 2 electrons. So boron goes into that new orbital. Corbin, son's name. Carbon goes into the new orbital. Nitrogen, same energy level. What happened? That new orbital type has to have multiples so that it can account for the rest of those multiplying through. And so when we look at that video, first energy level has 1 orbital type. That 1 orbital type looks like a sphere. Okay? You are responsible for the cartoon shape. We then go up in energy, so we'll go up in energy here. Here's our second energy level. We're going to repeat that past orbital type. So I have another sphere. But we said I need a new orbital type. That new orbital type is going to look a little bit different. And that difference in appearance is actually something that can help us out. That difference in appearance, it looks like a dumbbell, more or less. When I look at that first energy level, go back to that that sphere. Okay? What happens if I turn it? Can you tell that it was turned? No. And so that means for that particular type of orbital, the sphere orbital type, there is only 1 orientation. I know that sounds foreign. One orientation, which means there is only one way to represent that. There's one orbital for the sphere. So when I go up in energy to the second energy level, I repeat, I still get the sphere. Okay, I didn't do a very good job. It should be bigger. Right? But then I get a new orbital type. This new orbital type is that dumbbell. Can I tell if I turn it? Yes, which means there are multiple orientations. The orientations, you get the y, because everybody thinks that's the y-axis, the x-axis, and then the z-axis. Where's the z-axis? Three-dimensional, in and out of the plane. That's 3 orbitals. Since each orbital can hold 2 electrons, how many electrons should I be able to fit in this total section? 6. How many columns in that second weird-looking block? 6. Guess what that weird-looking block is filling? Those weird dumbbell shapes. So every element out there, the last electron, is going into a weird-looking dumbbell-shaped orbital. Okay? What happens as I go up in energy again? Close, not yet. Copy the past. Again, bigger. I get all these. And now I get a new orbital. What's the new orbital look like? Clover. The clover leaf times 5. Okay, because I'm not going to draw them all out. It's officially actually times 4, and then this one with a donut. Don't worry about that one. Okay, how do I know there's 5? How many electrons could you fit into an orbital?
2.
2. Look at that first energy level. How many columns are in that first energy level? First energy level.
2.
Columns in the first energy level. So where's the energy level? It's the row. So look at that row. How many columns do you have in that row? 2. Second energy level. We have 8 total, but be careful. The first 2 are RS. The last 6 are the P. Sorry, dumbbell. I didn't define them yet. Okay. This is our first energy level. It's hydrogen and helium. This is our second energy level. That orbital is going to fill our lithium and beryllium. What's going to fill those? Boron to neon. The dumbbells. Go up to the third energy level. We did red. Let's keep red. What's going to fill that one? Third energy, sodium and magnesium. What's going to fill those? Cool, aluminum to argon. Some people are picking this up. This is challenging. It's going to take some time. What's going to fill this next one? You'll be like, well, we just moved down one, right? If you move down one, you'd move to potassium and calcium. Do you think potassium and calcium are going to fill that goofy cloverleaf shape? No, why not? Yeah, this weird hand gesture thing is a little awkward, but yeah, absolutely right. If we look, those first 2 columns are a section of the periodic table. That section of the periodic table refers to that sphere shape. Those last 6 section of the periodic table refers to our dumbbell shape. When I get to that clover leaf, that better refer to another shape on the periodic table. Where's that? Scandium to zinc, Sc to Zn. How many columns are in that?
9.
Should be 10. Right? Remember, did I say in this class counting is hard? Okay, because counting is hard. Everybody laughs and go, it's not that hard. It's hard. It's hard. Okay, there's 10. Okay, each orbital can hold 2 electrons. How many orbitals do I need? Right? 2 times x equals 10, how many orbitals do I need? 5. How many did I say there were? Times 4 plus the weird donut looking one. There's our 5.
Wait, sorry, you said there's 10 where
In the center section, scandium, Sc to zinc, Zn. Okay? Neat. Okay? How does this help us dictate size? That's an awesome question. Think about it, and because we're done with time, figure it out. We'll talk about it either Monday or you can ask me in person. I'm fine with that too.